Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar.
Hello everyone, welcome to the course lecture 30 of the course Marine Renewable Energy Systems Analysis, Design and Development. I am Dr. Basangoda I. Patil, Assistant Professor in the Department of Civil Engineering, PDEU, Gandhinagar, Gujarat. In the previous lecture, we discussed hydraulic power take-off systems, including their working principles, major components such as hydraulic cylinders, accumulators, hydraulic motors and generators, as well as their advantages, limitations and practical applications in wave energy converters. While hydraulic PTO systems offer excellent force transmission and energy smoothing capabilities, they also introduce additional components, hydraulic losses, maintenance requirements and system complexity. To overcome some of these limitations, researchers have developed direct drive energy conversion technologies where wave-induced motion is converted into electricity with fewer intermediate stages. One of the most important technologies in this category is the linear generator. In today's lecture, we will study the fundamentals of linear generators, understand their operating principles based on electromagnetic induction, and study their major components and configurations. We will also discuss their advantages, limitations, and review several practical wave energy converter applications that employ direct drive linear generation technology. Before discussing the design of linear generators, it is important to understand why they were developed for wave energy applications. Traditional wave energy converters often use conventional rotary generators. However, these generators require intermediate transmission systems such as gearboxes, crank mechanisms, and hydraulic transmission systems to convert the oscillatory motion of the waves into rotational motion. Madam, I have taken, means, let me continue. Means you'll cut it, no, in between. Means I am changing the pen, it is not selected. Yes. While these systems work effectively, they induce additional mechanical losses, increase maintenance requirements, and add complexity, and overall PTO system becomes complex. Researchers therefore explored an alternative approach. Instead of converting linear motion into rotational motion first, why not generate electricity directly from the wave induced motion itself? This idea led to the development of linear generators, where the reciprocating motion of a buoy or translator directly produces electricity through electromagnetic induction. By eliminating gearboxes and hydraulic transmission systems stages, linear generators can potentially reduce losses and simplify the energy conversion chain and improve long-term reliability in offshore environments. Therefore, the main motivation behind linear generators is to achieve a more direct, efficient, and reliable conversion of wave energy into electrical energy. Let us now understand the basic concept and operating principle of linear generator. The idea is very simple. Instead of converting wave motion into rotational motion first, the wave induced motion is used directly to generate electricity. As shown in the flow chart, the process begins with the wave motion. The oscillating waves cause a component called the translator to move back and forth in a linear manner. This linear motion causes a change in the magnetic field passing through the generator windings. In other words, the moving translator creates a magnetic flux variation. According to the principle of electromagnetic induction, a changing magnetic flux induces an electrical voltage in the coils, which can then be used to generate electrical power. Therefore, energy conversion chain becomes very short. Wave motion drives linear translator motion and induces magnetic flux and variation, then electrical energy is generated. The most important point is that no intermediate rotational conversion is required. So, we eliminate rotational conversion components such as gearboxes, crank mechanisms, hydraulic motors, and several other transmission components. As a result, the direct drive concept offers a simpler energy conversion pathway with fewer moving parts and potentially lower mechanical losses. The next slide will examine the basic study basic structure and working components of a linear generator. Having understood the direct drive concept, let us now define the device that makes this possible. The linear motion electricity generator, in short called as LMEG. An LMEG is a generator that converts reciprocating linear motion directly into electrical energy using the principle of electromagnetic induction. Unlike conventional generators, which require a rotating shaft, a linear generator operates using a translator that moves back and forth and in a straight line. This motion creates a changing magnetic field which induces voltage in the surrounding coils. Let us look at the key features. First, it is a direct drive system, then meaning there is no need for gearboxes, crank mechanisms or hydraulic transmissions. Second, energy conversion occurs through linear translator motion, which is naturally compatible with the up and down motion produced by ocean waves. Third, the generator typically consists of permanent magnets of copper windings, and the magnets move relative to the coils, electrical energy is generated. Finally, because several intermediate transmission stages are eliminated, mechanical transmission losses are reduced, which can improve overall efficiency and reliability. The photographs shown here illustrate a prototype linear generator developed for wave energy applications. The moving magnet assembly travels uh, inside the cylinder which has copper winding, and the induced voltage can be directly used or conditioned through power electronics before being supplied to the electrical system. Therefore, an LMEG provides a simple and elegant way of converting wave induced motion directly into electricity while minimizing the number of mechanical components. Here these images show the various components. The first one is the rod which has permanent magnets called as N52 neodymium magnets, and another cylinder in which this magnetic rod moves forth and back is having a copper windings, and then the complete assembly is shown here. When this prototype was tested, when these linear rods were moved inside the cylinder, the LED bulbs connected were started glowing, indicating there is a production of electricity through electromagnetic induction principle. So, in the next slide, we will examine the electromagnetic principle that enables the electricity generation in linear generators. As the heart of every linear generator lies the principle of electromagnetic induction, which was first established by Michael Faraday. The fundamental idea is straightforward. Whenever there is a relative motion between a magnetic field and an electrical conductor, such as a coil, an electrical voltage is induced. This phenomenon is described by Faraday's law of electromagnetic induction, shown on the slide. The equation here is E is equal to minus N d phi by dt, where E is induced electromotive force or voltage, and N is the number of turns of copper coils. Then phi is the magnetic flux passing through the coil. Then d phi by dt represent the rate at which the magnetic flux changes with time. The equation tells us that electricity is generated only when the magnetic flux changes. For a linear generator, this change occurs naturally because the wave induced motion causes the translator, which contains permanent magnets, to move relative to the stationary coils. As the magnets move, the magnetic flux linking the coils continuously increases and decreases. This varying magnetic flux induces an alternating voltage in the windings. You will also notice the negative sign in the equation. This comes from Lenz's law, which states that induced voltage always acts in a direction that opposes the change that created it. So, this is a fundamental law of energy conversion. The important takeaway for wave energy applications is that the translator does not need to rotate. Simple back and forth motion is sufficient to generate electricity. Therefore, in a direct drive linear generator, the oscillatory motion of ocean waves directly produces changing magnetic flux, and that changing magnetic flux generates electrical power without requiring other components. The electromagnetic induction principle forms the foundation of all linear generator technologies used in wave energy converters. The main components of LMEG. Let us now examine the different components of LMEG. The figure here shows simple laboratory scale linear generator developed by Patil and Chandrasekaran Srinivasan. The first component is the translator here. The translator is the moving part of the generator and moves back and forth in response to the wave induced motion. Mounted on the translator are permanent magnets, typically high strength neodymium magnets such as N52 magnets shown in this figure. These magnets provide the magnetic field required for electricity generation. Surrounding the translator is a stator, which is the stationary part of the generator. The stator contains the coil windings, usually made up of copper wire. As the translator moves through the stator, the magnetic field passing through the coil changes continuously. This changing magnetic flux induces an electrical voltage according to Faraday's law. The system also requires a guide mechanisms to ensure smooth linear motion and maintain poor alignment between the moving translator and stationary coils. Finally, the generated electricity is collected through electrical output terminals, which connect the generator to the power conditioning and electrical systems. In summary, the translator and magnets create the changing magnetic field, and stator and coils convert that magnetic variation into electricity, and the guide and electrical systems ensure reliable operation. Although the concept appears simple, the performance of a linear generator depends strongly on the design and optimization of these individual components. Now, let us understand the working mechanism of a linear motion electricity generator. The entire energy conversion process can be explained in 5 simple steps. First one, ocean waves induce oscillatory motion in the wave energy device. In the example here shown, a Suzuka dolphin, a dolphin shaped bio-inspired floating platform which moves up and down here due to the wave action. Suzuka dolphin, this motion is captured here in the LMEG attached at the tail of it. Second, this wave induced motion is transferred through a linear generator. As a result, the translator inside the LMEG moves back and forth. When there is a linear motion here, this rod moves back and forth in this cylinder which has copper windings. That is why the magnetic flux is generated. And still the permanent magnets attached to the translator moves relative to the stationary coil windings. This relative motion causes the magnetic field passing through the coils to continuously change. According to Faraday's law of electromagnetic induction, this changing magnetic flux induces a voltage in the stator windings. Finally, the generated voltage can be connected to an electrical circuit, allowing electrical power to be extracted and supplied to the load or grid. And this figure illustrates this process clearly. The left side shows the wave induced motion of the floating device, this one. Suzuka dolphin is moving up and down in the front, and also here pitch and heave are coupled because at the tail Suzuka dolphin is hinged. So there is a heave and pitch coupling here. So because of that, there is a linear motion created because of wave action. That linear motion helps stator or steel rod which has permanent magnets to move inside the copper wire winded cylinder to create the required EMF. The key point to remember is that wave motion itself directly drives the translator. There is no gearbox, there is no crank mechanism and hydraulic circuit or rotary transmission stage is involved here. This direct conversion pathway reduces transmission losses and simplifies the overall energy conversion chain. Therefore, the energy conversion sequence can be summarized as wave motion inducing the linear translatory motion, then the magnetic flux variation, then which induces the voltage, then the electrical power output can be stored. This is the fundamental operating principle behind all direct drive linear generator wave energy converters. Among the different types of linear generators, the most widely used configuration in wave energy applications is the permanent magnet linear generators, commonly known as PMLG. These operators use high strength permanent magnets, typically neodymium ion boron or NdFeB permanent magnets, which provide very high magnetic energy density. Because of their strong magnetic field, they can generate electricity efficiently even at the relatively lower speeds associated with the ocean waves. The permanent magnet linear generators are generally available in two main configuration. The first is the tubular configuration and second is the flat linear configuration. In tubular configuration, the translator moves inside the inside a cylinder stator. In the flat linear configuration, the translator moves along a flat track. The choice depends on the device geometry and PTO architecture. The basic operating principle remains the same. The translator carrying permanent magnets moves linearly relative to the stator windings, and this changing magnetic field induces voltage in the coils through electromagnetic induction. One of the major advantages of permanent magnet generators is their high magnetic flux density, then which enables high power output from a compact device. They also offer a high power to weight ratio An important advantage for the offshore for an offshore systems where weight and structural loads must be minimized. Another benefit is that no external field excitation is required. Since the magnetic field is produced by permanent magnets, excitation losses are eliminated, leading to improved efficiency. As a result, permanent magnet linear generators generally provide high efficiency, generator stability and better suitability for low speed wave induced motion compared with conventional generator technologies. For these reasons, permanent magnet linear generators have become one of the most promising direct drive PTO technologies for modern wave energy converters. One of the most common configurations used in direct drive wave energy converters is the tubular linear generator configuration or tubular linear generator. In this arrangement, a cylindrical translator moves back and forth inside a tubular stator. As the translator reciprocates under wave action, the magnetic field changes relative to the stationary windings, generating electricity through electromagnetic induction. A major advantage of this configuration is its axisymmetric geometry, because the magnetic field is distributed symmetrically around the central axis. The generator experiences more balanced electromagnetic forces during operation. Then tubular design is also compact and mechanically robust, making it highly suitable for offshore environments where reliability is essential. As shown in the figure, the generator can be integrated directly with a floating buoy. The vertical motion of the buoy drives the translator, allowing the direct conversion of wave induced motion into electricity without intermediate mechanical transmission systems. Here in both the figure, cross sectional view of buoy and generator is shown. This is the magnetic assembly and this is the spar. In the cross section is shown here. Another important benefit is the reduction of transverse or radial forces. Reduction of transverse or radial forces. This improves translator alignment and reduces mechanical wear during the long term operation. The tubular configuration also offers high force density and energy density, meaning more power can be extracted from a relatively compact device. In addition, compared with some flat linear generator configuration, tubular systems often exhibit lower cogging forces, resulting in smoother motion and improved energy capture. Because of these advantages and compactness, high force density, good alignment characteristics and reliability, the tubular generator has become one of the most widely investigated direct drive generator designs for wave energy applications. The experimental system shown here is reported by Trudell in the year 2010 and other co-workers is the well-known demonstration of its technology. Having understood the operating principle of linear generators, let us now discuss why direct drive systems have attracted significant attention in the wave energy research. The biggest advantage is the elimination of gears, hydraulic circuits and other rotary transmission components. In conventional PTO systems, each additional component introduces energy losses, maintenance requirements and potential failure points. Direct drive generators avoid many of these issues by converting wave motion directly into electricity. As a result, mechanical and transmission losses are significantly reduced, leading to improved overall efficiency. Another important benefit is the reduced number of moving parts and lower maintenance requirements, improves operational reliability, which is particularly important in offshore environments where maintenance is expensive and difficult. Direct drive systems also offer improved survivability because there are fewer mechanical components exposed to cyclic loading, wear and corrosion. A further advantage is that they are naturally suited for the low speed and low frequency motion produced by waves. Instead of increasing speed through gears or hydraulic system, the generator is designed to operate directly with the available wave motion. Therefore, the key idea behind direct drive technology is simplicity. By removing intermediate conversion stages, we obtain a system that is more efficient, more reliable and easier to maintain over its operational life. For these reasons, direct drive linear generators are increasingly being viewed as one of the most promising PTO technologies for future wave energy converters. Although linear generators offer several advantages, they also face important engineering and offshore challenges that must be addressed before large scale deployment. Let us first look at the engineering challenges. One major challenge is the large translator mass. Since permanent magnets are mounted on the moving translator, the moving assembly can become quite heavy. This increases inertia, structural loads and overall system cost. A second challenge is the low frequency nature of ocean waves. Typically, wave frequencies are only about 0.05 to 0.3 hertz because electromagnetic induction depends on the rate of change of magnetic flux. These low operating speeds can limit the generated voltage and output. Another issue is variable speed operation. Ocean waves are irregular, causing continuous fluctuations in velocity, frequency and displacement. There are fluctuations. So consequently, the electrical output of the generator is also highly variable. The use of neodymium permanent magnets presents an additional economic challenge. These magnets provide excellent performance but are relatively expensive and depend on rare earth materials. Finally, electrical control can become complex. Power electronic systems such as rectifiers, converters, maximum power point tracking and real-time control algorithms are often required to deliver the stable electrical output. Now let us consider the offshore challenges. The first is corrosion environment. This is the continuous exposure to seawater can degrade metallic components and reduce long-term reliability. Sealing is another critical issue. The generator must be effectively protected from the seawater ingress. Any seal failure can lead to severe damage to electrical and magnetic components. In addition, extreme waves and storm conditions can impose very large force on the device. Therefore, structural reliability and survivability becomes key design requirements. So, while direct drive linear generators eliminate many mechanical transmission losses, they induce challenges related to low frequency operation, magnet cost, control requirements, and harsh offshore environments. Addressing these challenges remain one of the major focus areas of current wave energy research. One of the most important challenges for linear generators is the highly variable nature of ocean waves. Unlike conventional power plants, ocean waves are inherently irregular and stochastic. Wave heights, periods, and wave frequencies continuously change with weather and sea states conditions. Typically, ocean waves frequencies lie in the range of about 0.05 to zero point 0.3 hertz, which means that the motion driving the generator is both slow and highly variable. As a result, the translator inside a linear generator does not move at a constant speed. Instead, its velocity changes continuously according to the incoming wave conditions. This directly affects the electrical output of the generator. For example, if the translator speed varies, the induced voltage also fluctuates. Similarly, changes in wave frequency produce variations in the electrical frequency. And irregular wave heights lead to uneven power production. While random sea states can reduce overall power quality and grid compatibility. Therefore, unlike conventional generators that operate at nearly constant speed, wave energy linear generators must continuously adapt to changing ocean conditions. To address this challenge, modern systems often incorporate power electronics, energy storage devices, and advanced control algorithms that help regulate the output and improve power quality. The key takeaway from this slide is that variable wave conditions are not only merely an environmental issue, they directly influence the electrical performance of the linear generator and therefore must be considered in the design of the PTO system. One important challenge of linear generator is that the electrical output is not directly suitable for grid connection. As we discussed in the previous slide, ocean waves are irregular, causing continuous variation in voltage, current, frequency, and power output. Therefore, a power conditioning system is required between the generator and the electrical grid. The process begins with the linear generator producing a variable three-phase AC output. The first stage is the AC to DC converter, also known as a rectifier. This converts the variable AC power to DC power. Next, a DC-DC converter regulates the voltage level and maintains a stable DC link despite fluctuations in wave conditions. The final stage is the inverter, which converts the regulated DC power back into AC power with the required voltage and frequency for grid synchronization. In modern wave energy systems, these power electronic stages are coordinated by a control system. The controller performs several functions, including voltage regulation, frequency stabilization, maximum power point tracking or MPPT, and protection and continuous performance monitoring. The overall objective is to ensure that Although the generator output may fluctuate due to changing wave conditions, the electricity delivered to the grid remains stable and high quality. Therefore, power conditioning systems play a critical role in direct drive wave energy converters. They transform the variable electrical output of the linear generator into grid compatible power while maximizing energy capture and protecting the systems. In summary, the energy conversion chain becomes wave motion, linear generator, then rectifier, then DC link, then inverter, then grid quality electricity. This power electronic interface is one of the key enabling technologies that makes a direct drive wave energy system practical for real world applications. Let us now discuss an important concept in wave energy conversion: overall system efficiency. A wave energy converter consists of multiple stages, and each stage introduces some level of energy loss. Therefore, the final electrical power delivered to the grid depends on the efficiency of every component in the energy conversion chain. The first stage is the hydrodynamic capture efficiency, which represents how effectively the device extracts energy from the incoming waves. This is often the largest source of losses, with typical efficiencies ranging from about 20 to 60%. The next stage is the PTO efficiency, which represents the effectiveness of the mechanical or hydraulic or electrical power takeoff system. Typical values range from about 80 to 95%. The generator efficiency is generally high, typically between 85 to 98%, depending on the generator design and operating conditions. Similarly, power electronics converters such as rectifiers, DC-DC converters and inverters usually operate with efficiencies of about 95 to 98%. Finally, electrical transmission systems induce small additional losses with efficiency generally between 95 to 99%. An important point to remember is that these efficiencies do not simply add together, instead they multiply. The overall efficiency is therefore expressed as overall efficiency is hydrodynamic capture efficiency into power takeoff efficiency into generator efficiency into power electronics efficiency into transmission efficiency. This means that even a small losses at each stage can accumulate and significantly reduce the final electrical power output. For example, a highly efficient generator alone cannot guarantee high overall performance if the hydrodynamic capture efficiency is low. Therefore, successful wave energy converter design requires optimization of the entire energy conversion chain rather than focusing on a single component. The key takeaway is that system level efficiency is governed by the combined performance of all stages, from wave capture to final power delivery. Let us now look at one of the important performance indicators in wave energy system: hydrodynamic efficiency. Hydrodynamic efficiency represents how effectively a wave energy converter captures the available energy from incoming ocean waves. It is defined as the ratio of power absorbed to the wave power, incident wave power. Here P wave is incident wave power and P absorbed is the power absorbed by the wave energy converter. P wave represents the total power available in the incoming waves, while P absorbed represents the power actually captured by the wave energy converter. Therefore, hydrodynamic efficiency of 50% means that the device successfully captures half of the available wave energy. Several factors influence this efficiency. The first is the absorption capability. A device must effectively intersect and interact with the incoming waves to extract energy. The second factor is the resonance matching. Maximum energy capture occurs when the natural period of the device is close to the dominant wave period. Under resonance condition, the device oscillates with larger amplitudes and absorbs more energy. Another important factor here is radiation damping. As a floating body oscillates, it generates its own radiated waves. These waves influence the energy exchange process and affect the amount of power that can be extracted. Finally, the device geometry plays a major role. Parameters such as the shape, size and draft determines how the structure interacts with ocean waves and therefore strongly influence hydrodynamic performance. An important observation is that even if the PTO and generator are highly efficient, the overall system performance will still be limited if the hydrodynamic efficiency is low. Therefore, the first step toward achieving high electrical power output is to maximize the amount of wave energy captured by the device itself. In summary, the hydrodynamic efficiency measures the effectiveness of wave energy capture and forms the foundation upon which all subsequent energy conversion stages are dependent. Having discussed hydrodynamic efficiency and overall system efficiency, let us now focus on the electrical efficiency considerations. Electrical efficiency of the linear generator based on wave energy converters is important. Even after successfully capturing wave energy and converting it into electricity, some energy losses inevitably occur within the electrical system. Understanding these losses is important for improving overall performance. The first type is copper losses. These are the well-known I squared R losses that occur in the stator or translator windings due to electrical resistance. A portion of the electrical energy is converted into heat, reducing efficiency. The second type is eddy current losses. Changing magnetic flux field induce circulating currents with the conducting materials such as magnetic cores and metallic components. These unwanted currents generate heat and consume useful energy. Another important loss mechanism here is the hysteresis loss. During operation, the magnetic core repeatedly undergoes magnetization and demagnetization. This process dissipates energy within the magnetic material and contributes to the efficiency reduction. We also encounter magnetic leakage losses. Ideally, all magnetic flux should pass through the through the intended magnetic circuit and interact with the coils. However, some flux escapes and does not contribute to the power generation, reducing the useful electrical output. Finally, the power electronics losses is also important to be considered. Rectifiers, converters and inverters are necessary for conditioning electrical output, but switching and conduction process within these devices introduce additional energy losses. Because of these factors, the engineering objective is not only to generate electricity, but to maximize the efficiency of the entire electrical conversion chain. This chain can be achieved by optimizing the machine design, including the windings, magnetic core and permanent magnets, minimizing parasitic losses and employing high efficiency power electronic converters, and uh, implementing advanced control strategies such as the maximum power point tracking, in short called as MPPT. In summary, careful electrical design is essential to ensure that the maximum possible fraction of captured wave energy is delivered as useful electrical power. Until now, we have discussed efficiency from the perspective of hydrodynamics, generators and power conversion. However, when comparing different wave energy converter concepts, researchers often use another important performance indicator known as the capture width ratio, or CWR. Capture width ratio measures how effectively a wave energy converter extracts energy from the available wave source, such as incident waves. The capture width ratio defined as power absorbed by power wave, incident power wave, into B, where the power absorbed is the power absorbed by the wave energy converter, and P wave is the incident wave power per meter of wave crest, and B is the characteristic width of the device in meters. Physically, capture width ratio compares the effective energy capturing width of a device with its actual physical width. For example, if a device is able to absorb as much energy as is available in a wave front wider than its own dimension, the CWR can approach or even exceed unity in certain point observer configurations. A high CWR generally indicates better hydrodynamic performance and more efficient utilization of the incoming wave energy resource. This metric is particularly useful because it allows researchers to compare different wave energy converter technologies of different sizes and geometries on a common basis. The table on the right side shows some typical values reported in the literature. Oscillating water column, or OWC devices typically exhibit CWR values between 0.1 to 0.4, and attenuator type devices generally fall in the range of approximately 0.2 to 0.6, and point absorbers often achieve the highest values ranging from around 0.3 to 1, in some cases approaching 1 or exceeding 1 under favorable operating conditions. Therefore, CWR has become one of the most widely used performance metrics in wave energy research for evaluating and comparing the device effectiveness. In summary, while efficiency tells us how well energy is converted, capture width ratio tells us how effectively a device captures energy from the available wave resource. Let us now conclude this lecture by reviewing the key concepts we have discussed regarding linear generators for wave energy conversion. First, we have learned linear motion electricity generators directly convert linear wave motion into electricity. Unlike conventional systems, no gearbox, crank mechanism or hydraulic transmission is required. We then understood the principle of electromagnetic induction, where the relative motion between the permanent magnets and the coil produces an induced voltage according to Faraday's law. Next, we discuss the major components of linear motion electricity generator, that is permanent magnets, stator windings, guide mechanisms and electrical output terminals. We also studied permanent magnet linear generators, which are widely used because they provide high magnetic flux density, improved efficiency and reliable operation under the low speed oscillatory motions. Another important concept was the direct drive approach, which eliminates intermediate transmission systems. This significantly reduces mechanical losses, decreases maintenance requirements and improves overall system reliability. However, we also saw that ocean waves are inherently irregular. As a result, linear generators experience continuously changing speeds, voltage and frequencies and the power outputs. These variations can create important control and power conditioning challenges. To address these challenges, modern wave energy systems employ power electronic converters, inverters, control algorithms, and maximum power point tracking strategies to deliver stable and grid compatible electricity. Finally, we have discussed performance evaluation metrics such as overall efficiency, hydrodynamic efficiency, and capture width ratio, which help engineers assess and compare wave energy technologies. In summary, the linear generators represent one of the most promising direct drive PTO technologies because they offer high efficiency, reduced mechanical complexity, and improved reliability. At the same time, their successful deployment depends on effective electrical control, power conditioning and adaptation to a highly variable ocean environments. Thank you.